In lesson 5, we're going to learn two new theorems called the remainder and factor theorems. And these theorems are going to be used in the next few lessons to learn how to be able to solve polynomial equations. So in order to do that, we're going to be using a lot of synthetic division. So I just want to refresh your memory on how to use synthetic division. So if you remember this first example here, first thing you want to do is you want to set up your L. And what you're going to do is whatever number you're dividing by, it always has to be a linear term in order to use synthetic division, and it's always going to be the opposite number. So instead of x minus 3, I'm going to put a 3 out in front of my bracket here. Then I'm going to take the coefficients of each of these, and remember that this polynomial on top has to be in standard form, because if I'm missing one of the terms, you have to remember to put a 0 in. So I'm not missing any of the terms because it goes from x to the third, x to the second, first, and then the constant. So I can just take and put in the coefficients just as I see them. So I have 3, I have positive 5, I have negative 10, and I have positive 1. And then the process of using synthetic division is first you take and you slide the first term down. And then what you're going to do is you always multiply diagonally. So I'm going to multiply the numbers diagonally. So I have 3 times 3 is going to give me 9. And then you're going to add the numbers vertically. So that means I add 5 plus 9, which is going to give me 14. And then you just continue the process. So 14 times 3, so I'm multiplying diagonally. So 14 times 3 is going to give me 42. And then I add negative 10 plus 42 is going to give me 32. And then again, 32 times the 3 is going to get me 96. And then you're adding 1 plus 96 gives me 97. So this number that's left is always the remainder. So since we got a remainder of 97, that means that x minus 3 does not go into my original polynomial, or the original polynomial is not divisible by x minus 3 since you had a remainder. So your answer, remember, is always 1 less than the degree of the original. So since the highest exponent in this one is 3, this was a degree 3 polynomial, and I divided by a degree 1 polynomial, or a linear term, which means my answer needs to be a degree 2. It needs to be 1 less since I divided by an x to the first, or degree 1. So that means you're going to start this off with a 3x squared. Then it's going to be plus 14. So I'm just looking at these numbers here. 14x. And then your last one is going to be plus 32. And then your remainder, you write it as 97 over whatever you divided by. So that would be the answer to this. So now let's look at the actual theorem. So the first one is called the remainder theorem. And basically what the remainder theorem says is instead of actually having to go through this synthetic division process to get the remainder, you could have actually just taken this number that I placed out in front, and I could have just taken that and I could have plugged it into this polynomial on top, and you would have seen that you actually get out the remainder. So it's a theorem that's saying that if I take 3 and I plug it into the polynomial on top for x, so if I did 3 times 3 raised to the 3 plus 5 times 3 squared minus 10 times 3 plus 1, you would get 97. So basically, that's just another way of finding the remainder. So if you had some expression that was, or some polynomial that had a really high exponent, like let's say 200, you wouldn't want to have to go through synthetic division because that means you would have to include all of those terms from the exponent of 200 all the way down to 0. So you can use this theorem as a shortcut to figure out what the remainder is. So the remainder theorem says that if a polynomial, so let's say y, so if we have some polynomial y is divided, so if a polynomial y is divided by x minus k, then the remainder r is found by substituting k into the polynomial. So you just plug in k into the polynomial, and that whatever number you get is the remainder. That's what this theorem is saying. So k, notice that I have k is what I substitute in, and it's saying that if it's divided by x minus k. So you're always going to plug in the opposite sign for whatever k is. So just like this example up here, if I could have just taken and I could have plugged in 3, and you would have gotten 97. So that means the remainder is actually equal to plugging in whatever the opposite sign of whatever you're dividing by. So instead of x minus 3, you would plug in 3, and that would get you the remainder. So the next theorem is actually kind of a follow-up to the remainder theorem, and it's kind of like, why would we care to find the remainder, you might be thinking. And the reason why we care to find the remainder of any type of polynomial is because if the remainder is some number other than 0, that means that that factor or that number or that expression that we divided by is not a factor to the polynomial. So what happens is if you get out 0, so like in this example, if I would have gotten out 0, that means that x minus 3 goes into this polynomial. It also means that x minus 3 is a factor of that polynomial. So it's like if I take 16 and I divide it by 4, I get a remainder of 0 because 4 is a number that goes into 16. It's a factor of 16. If I take 16 and I divide it by 5, I'm going to get out a remainder because 5 is not a factor of 16. So that's kind of what's happening here. The remainder is actually going to be really important in determining which expressions are factors. So the next theorem is called the factor theorem because what the factor theorem says is that if a polynomial, so a polynomial has a factor x minus k if and only if the remainder is 0 when the polynomial is divided by x minus k. So x minus k is a factor if and only if the remainder is equal to 0 when the polynomial is divided by that factor. So basically, another way of thinking of this is if we kind of combine the two theorems here, if we want to determine if some expression or some x minus k is a factor, a shortcut would be, instead of actually having to go through and do the synthetic division and seeing if you get the remainder of 0, another way of doing it is to take k and you can plug it into the polynomial. If you get 0 when you plug k into the polynomial, that means that k is a factor. So let's go ahead and just write that kind of as like a follow-up. So basically what this means is if we plug k into the polynomial and get 0, then x minus k is a factor of the polynomial. So that basically kind of combines both theorems. So the remainder theorem is if you plug in k, then that means that that's whatever you get is the remainder when you divide by x minus k. And the factor theorem says that as long as you get a remainder of 0, that means that x minus k is a factor. So if we plug in k and we get 0, x minus k is a factor. So let's look at some examples. And I'm going to show you kind of using both ideas here, using synthetic division and the remainder theorem. So if you go to the next page, we have our first example has some different parts. Our first part here is to show that x is a solution of y. So we have x equaling -3. So if x equals -3 is a solution, that means that x plus 3 has to be a factor of my equation. And it also means that when I divide by x minus, so if you divide by x minus -3, which is really going to be x plus 3, then the remainder has to equal 0. So in order for x equals -3 to be a solution, that means the remainder has to be 0 when you divide by the factor. So keep in mind, if x equals -3 is the solution, then, so like if this is the solution, then x plus 3 is the factor. So factors are always in parentheses. We have the expression. This would be like parentheses times parentheses equals the entire expression. X equals -3. X equals tells me that that's the solution, and it's always going to be opposite signs. So if I want to show that x is a solution, so I'm going to do part A, I can do this two ways. I have to basically show that if I were to divide this expression by x plus 3, then the remainder equals 0. So you can show the remainder equaling 0 two ways. You can use synthetic division. So I can do this using synthetic division. And what you do is you take and you divide by whatever this is. So if you're dividing by x plus 3, that really means you have a -3. So you're really dividing by the solution. So I would take and I would put each of these coefficients up. So I have 2, 11, 18, and 9. And then I start the process, carry down the 2, multiply, we get -6. Add 11 minus 6 is going to give me 5. Multiply -3 and 5. So -15. Add these up. We get 3. 3 times -3 gives me -9. When you add, you get 0. So remember, this number at the end is the remainder. So since my remainder equals 0, that means that x equals -3 is a solution to this equation. Because if you divide by its factor, x plus 3, which is what we did, we got a remainder of 0. So if x plus 3 is a factor, then x equals -3 has to be a solution. So we have remainder equals 0. Therefore, x equals -3 is a solution, and x plus 3 is a factor. So factors are always the things that you would set equal to 0 to solve. So if you imagine taking x plus 3 and setting it equal to 0, and solve it for x, you would get x equals -3. So the factor is never has an equal sign. And it's always the opposite as the solution, because you have to imagine basically like undoing the process of setting it equal to 0 and solving. So that's using synthetic division, so that's one way. The other way is to go ahead and to use the remainder theorem. So I can say, by the remainder theorem, that if I take and I plug in the -3, then and I get 0, then that means my remainder is 0, which means that if my remainder is 0, then I have x plus 3 is a factor and x equals -3 is a solution. So I'm going to take my equation and I'm going to substitute x equals -3 in. So I'm going to go ahead, I'm going to take y, I'm going to plug in -3. So wherever you see an x, you're just replacing it with a -3, keeping in mind your parentheses because you have to make sure that you're entering these correctly in your calculator. Anything that's being a negative being squared has to become positive. So when you go ahead and you do this, you end up with y equals 0. So that means that the remainder equals 0. So therefore, x equals -3 is a solution, and x plus 3 is a factor. So that's the first part, showing that you have a solution. So basically, we showed the solution and I also showed the factors. So part B is asking you to find all of the factors. So what that means is, so far, I divided everything by x plus 3, and I found that x plus 3 is a factor because the remainder equals 0. So for part B, I already know one of the factors. So I know that x plus 3 is a factor because we divided the polynomial by x plus 3 and got a remainder equal to 0. You could also say that we use the remainder theorem, and by the remainder theorem, when we plugged in -3, the opposite of +3, we got 0, which means that the remainder is 0, which means that x plus 3 is a factor. So you could use either way. So then what that means is my original equation up there, so I have y equals 2x to the third. So this is just the equation from up top. Is the same thing as saying x plus 3 times some other expression. So if you think about it, if I take this first polynomial and I divided it by x plus 3, whatever I have left has to be what my other factor is, or what else I can multiply x plus 3 by to get the original. So if you look, right here is where I divided my original polynomial by x plus 3, and what I got out, so the answer to my division, was actually going to be 2x squared, because it's always one left, one exponent less, plus 5x plus 3, and the remainder was 0. So what that really means is 2x squared plus 5x plus 3 times my x plus 3, since I divided by -3, is actually equal to the original. So since x plus 3 was one of the factors, my remaining factor is actually this piece here. So 2x squared plus 5x plus 3. So it does tell us to find all of the factors. So I know that these two expressions multiplied will get me back to the original. But you have to look if you can factor further. And if you look, I have x plus 3, and I can break this part here up. So what you're going to do is this is going to be a factor by grouping because you have a leading coefficient not equal to 1. So you're going to multiply those two numbers. 2 times 3, we get 6. And you need to find two numbers that multiply to 6 but add to 5. So your answers are going to be positive 2 and positive 3. So you're going to rewrite this middle term using 2 and 3. So I'm going to have 2x squared plus 2x plus 3x plus 3. And I'm going to go ahead and split it. I'm just going to kind of carry this other stuff down. So I'm going to factor out a GCF here. I can factor out a 2x. I'll be left with an x plus 1. And then I can factor out a 3, and I'll be left with an x plus 1. And then I just, again, carry down this other stuff. So we have x plus 1 is coming outside of the parentheses. I'd be left with a 2x plus 3. So your factors of this equation are going to be these three things. It's going to be x plus 3, x plus 1, and 2x plus 3. Those are the three things that would multiply to get you the original. So those are the factors. And then the last part here is asking you to find the solutions. So the solutions mean take your factors when they're all multiplied and set them equal to 0 and solve it. So since I have these are my factors, this is the equation in factored form. So for C, you're going to take your equation and you're going to set it equal to 0 and you're going to solve it. So you're going to go ahead and you're going to take x plus 3, x plus 1, 2x plus 3 equals 0. And when we say the solutions, we're actually talking about something that has to do with the graph. So we're really talking about also the zeros, meaning when the equation equals 0. So when we're saying solutions, we're talking about when does the equation equal 0 for this. So then at this stage, once you have your factors, you can set each piece equal to 0. So x plus 3 equals 0, x plus 1 equals 0, and 2x plus 3 equals 0. And you solve each of these. So we get x equals negative 3, x equals negative 1, 2x equals negative 3. Divide everything by 2, you get x equals negative 3 over 2. So here are your solutions or your zeros to this equation. So when the equation equals 0. So let's do one other example with this just to show you again how these theorems work. And then we will pick up on more of the application of these theorems in the next lesson. So one last example here. We need to show in this example that x minus 2 and x plus 3 are factors of this equation. So what we want to do, there's a couple ways that you can do this. You can use either the remainder theorem or you can use synthetic division to show that you get a remainder of 0. So whenever you're trying to show that something's a factor, that means that you need to show that the remainder equals 0 when you divide. So you can either, so there's two ways of doing this. So there's two methods that you can do this. You can either use synthetic division, and show that the remainder equals 0. Or the other method that you could use is to use the remainder theorem like I did in that last problem. So basically the two methods I'm writing down are the two methods that I did here. I use synthetic division, or you use the remainder theorem and you plug in the opposite numbers and show that you get 0. So, or you can use remainder theorem and show that you get 0 when you plug in positive 2 and negative 3. So if you're looking, the factors are x minus 2 and x plus 3. So that means I'd have to plug in 2 and plug in negative 3 and get 0. So I'm going to use method number 1 just to, again, reinforce synthetic division. And if you wanted, though, keep in mind that you're always welcome to use method number 2. It totally works. It's just a matter of preference, and I just want to review synthetic division with you. So I'm going to use method 1. And what I want to do is I want to show that, first of all, I'm going to show that x minus 2 is a factor. So my first step here is going to be to show x minus 2 is a factor of 2x to the 4th plus 7x to the 3rd minus 4x squared minus 27x minus 18. And I think there might be a typo up here. This should be minus 18. So just make sure you fix that. So I want to show that it's a factor of this expression. So what I'm going to do is I'm going to go ahead, I'm going to divide by 2, or in the synthetic division put 2. Really what I'm doing is I'm dividing by x minus 2, but really what always goes here is the solution. So it's the 2, and you're going to put your coefficients, so 2, 7, negative 4, negative 27, negative 18. And then you're going to start the process. So we're going to carry down the 2, multiply, we get 4, add these, 11. 11 times 2 gives me 22. Negative 4 plus 22 gives me 18. So remember, I'm multiplying diagonally, adding vertically. So 18 times 2 gives me 36. I add these. So negative 27 plus 36 gets me 9. 9 times 2 gets me 18. Add these, you get 0. So that means, since I got a remainder of 0, x minus 2 is a factor. So therefore, x minus 2 is a factor of this expression, 2x to the 4th plus 7x to the 3rd minus 4x squared minus 27x minus 18, because the remainder was 0, or the remainder equals 0 when we divide by x minus 2. So what that also means is that I can rewrite 2x to the 4th plus 7x to the 3rd minus 4x squared minus 27x minus 18. I can rewrite that as, if you go up here, remember my answer to this division is actually going to be 2x to the 3rd, 1 less power, 11x squared plus 18x plus 9 by looking at what I got out. So that means the original is equal to x minus 2, since x minus 2 is what I divided by, times whatever my answer was. So 2x to the 3rd plus 11x squared plus 18x plus 19. Oops, plus 9. So that means that instead of using this original and dividing that by the second factor, x plus 3, what you can do is you can divide what you're left with. So since this original 4th power polynomial has factors of x minus 2 and 2x to the third plus 11x squared plus 18x plus 9, that means that since it says that I need to show that x plus 3 is also a factor, x plus 3 must also be a factor of this polynomial. So x plus 3 must be a factor of this polynomial if it's a factor of the original polynomial. Because what the question asked was for us to show that x minus 2 and x plus 3 were factors of the entire thing. And if I'm showing that when I take out the factor x minus 2, I'm left with this, that means that x plus 3 has to be a factor of that expression. So what I'm going to do, instead of showing that x plus 3 is a factor of the original, I'm going to go ahead and I'm going to show that x plus 3 is a factor of what I'm left with, because it has to work in there in order for it to be a factor of everything, since I already took out the first factor that had to work. So my second part here is going to be to show x plus 3 is a factor of 2x to the third plus 11x squared plus 18x plus 9. So we're going to go ahead and we're going to use synthetic division. So you put your coefficients. You're going to carry down the 2, multiply 2 times 3, we get negative 6. Add these up, you get 5. 5 times negative 3 is 15. 18 minus 15 is 3. 3 times negative 3 is negative 9. Add those up, you get 0. So that means, again, that x plus 3, so therefore x plus 3 is a factor of both expressions. So both 2x to the third plus 11x squared plus 18x plus 9. And so it's a factor of what I just divided it by because I got a remainder of 0. But since this polynomial is a factor of the original, that means that x plus 3 is also a factor of the original, since it's a factor of this 2x to the third plus 11x squared plus 18x plus 9. So I also know that x plus 3 has to be a factor of the original here. 2x to the fourth plus 7x to the third minus 4x squared minus 27x minus 18. Because the remainder is 0. So the last thing I want to just show you is that I could take this original. So since my answer here that I got out was 2x squared plus 5x plus 3, when I divided the degree 3 by a linear term, I got out a degree 2. That means that the original, so this original 2x to the fourth plus 7x to the third minus 4x squared minus 27x minus 18 is the same thing as saying x minus 2, because I divided it by x minus 2, times x plus 3, since I showed x plus 3 is a factor. So x minus 2 times x plus 3, because I basically took that entire thing and I divided it by x minus 2. I divided it by x plus 3. And then I'm left with 2x squared plus 5x plus 3. And you could actually factor this further to show that all of the factors of this would be x minus 2 times x plus 3, since those are the two that we showed are factors of the original. And when we divided by x minus 2, remember we got this expression here, and then I divided that by x plus 3. So I took that and I divided it by x plus 3, which got me this expression here. So that means my factors, x minus 2 times x plus 3, times what I got out, is the same thing as the original. But keep in mind, you can divide, or you can factor this further. So that would be factors of x plus 1 and 2x plus 3. And the best way to go about factoring that would be to use factor by grouping. So you would multiply the 2 and the 3, figure out what numbers, multiply to 6 and add to 5, and then regroup and then do GCF factoring. So basically, these are all of the factors of my original. I know I took this a step further, but you will have to do this in the next lesson. So it's important that you understand how it works.